Hello, friends. This is a video about refraction and Snell's law. The logic is going to come quickly. Please stop the video to take notes or rewind it if something doesn't make sense. When a wave goes from one medium to another, for instance, let's say air to water, the compressions will come in at some angle. So these are called the wave fronts. So first, we're going to go over terminology. The line at which it comes in, right? The wave speed, the velocity, which also represents the distance between peaks, which is the wavelength, it'll be perpendicular to the wavefront. So imagine a bunch of water waves coming in or compression waves coming in. Clearly, the direction of the wave is forward, right? But the wave is here. And this compression wave is all moving forward like this. Pause and let that make sense. That's it, right? So this is called the ray. This is called the wavefront. When it hits the water, I hope it's clear that the water is faster. This is V2, this is V1. We're going to do any given material's velocity 1 and velocity 2. Now, velocity 1 could be greater than velocity 2, and velocity 2 can be greater than velocity 1, right? These each have a different outcome. In general, though, the outcome is that if the each wavefront is an input into the new medium, right? These are each inputs, right? That's the whole point. Velocity must change. Frequency is constant. This is rule number 2, right? I lost my whiteboard. Here I come. Got it back. That shocked me. You guys got my shock face. Rule number 2 is, of course, that frequency is constant when a wave hits a new medium. Great. So what does that do to the wave? Well, that makes the wavelength increase. So if velocity 2 is greater than velocity 1, then the wavelength is greater. And here, the wavelength would be smaller. That in turn does something different, does something else. It changes the angle. If I go to water, it's this one. The velocity is bigger, therefore the wavelength is bigger. And because these are the new input, for the wavelength to be bigger, the angle has to change for the geometry to fit. So this wavelength 1 has to fit in, and then I have a new wavelength, wavelength 2, which means that the ray has to bend like this. So now I have wavelength 2, wavelength 2. Those are supposed to be the same distance. Wavelength 1, wavelength 1, wavelength 1. For it to spread out, it has to bend. So that means the angle has to change. So refraction is this, right? Speed change creates wavelength change, creates angle change. Now we have to be very, very careful of how so this is all it's geometric. And it comes from rule number 2. So this is a geometric alignment coming from the fact that frequency is constant. The First medium is the input to the second medium, is the logic here, which you guys hopefully already are comfortable with and know. So here the angle must be different. And we're going to see that theta 2 is greater than theta 1 here, and theta 2 is less than theta 1 if it's slower. So slower means smaller angle, faster means larger angle. That's the concept, really important concept for refraction. Write that down and put it in a box. You can even write this down as the logic, right? This is the geometric logic, right? So it's a physical mechanism that has a geometry, and that's what's happening here. Now you might see this angle does get bigger, but bigger with respect to what? So we have to be really, really careful that we draw this correctly. It's bigger with respect to this line here, which we call the normal line. Normal, like normal force, means perpendicular, right? Perpendicular to the boundary, right? So the angle is actually this angle here, theta 1, and this angle here is theta 2. Maybe I'll label that in a different color. Theta 2 is here. Theta 1 is here. The normal line is here. So ultimately, all we need to do is draw the ray, draw the angle, and draw the normal line. We don't need to draw the wavefronts. We just prove this, that this angle increases because they have to spread out if it's faster. If it's slower, what we'll see is that this has to bend inward and therefore becomes more vertical, more perpendicular. So let's kind of clear this up and formally define it. So all we need to do is you don't need to draw the ray fronts. Draw rays, which represent the velocity vector, and angle with respect to normal line. So really a step one is to draw the normal line, right? It's perpendicular to this to the boundary. Step two, draw the angle, draw theta 1, and step 3, solve for theta 2 and draw it opposite the normal line. And I'll explain what I mean by that. The normal line is just a fictional line. So when the rays go through, I'll draw it right now. You draw the normal line, it's perpendicular to the surface. The ray goes here. Say V2 is smaller, then V1, then theta 1 will be closer to the normal line, right? But it doesn't bounce off. This is wrong. Don't ever draw it bouncing off. It goes through, of course, because it has momentum, right? So it's going this way. It's going down and right. So here it's going down and right, just slightly more down than right. And I'm sure we can do some conservation of momentum or conservation of energy to figure that out. Probably momentum, because momentum's got the vector thing. Cool. So if theta 1 is bigger, theta 2 is smaller, then it will bend, draw it opposite the normal line, going through the normal line. Please don't ever have it reflect off the normal line. Remember that right now. This is the most important part about drawing it. Now the math. Again, pause that if you need to, go over that. That was everything. Now the math. So I'm going to derive this real quick. Actually, I'm just going to tell it to you. I will derive it. Actually, I'm going to derive it. Might as well. So in case you wanted to sort of see it on your own. So we have to label this properly. So I'm going to do faster. All right, so this is V2 faster than V1. And we want to look at this section right here. So if you want to skip this derivation, just go straight to, so this is theta 1. You can just fast forward until I draw something in a box. And then this is, sorry, that's lambda 1, and this is lambda 2. Now, you might see that lambda 2 is bigger, lambda 1 is smaller, and we have two right angles that share, two right triangles that share a hypotenuse. That's huge. So we're going to call that hypotenuse D as some distance, and they share it. And that's kind of the whole point of this Snell's law. And so what we get is if we draw the normal lines, right? Now, where do I want to draw the normal line? Well, let's see. My ray is coming in like this, right? So this is my ray like this, which means that my normal line has to come here. And that means my ray 2 comes out kind of like this, right? So my second ray comes out like this. So it means my other normal line is here. This is my ray 2 coming out. So each boundary has a ray coming out. There's obviously infinite rays coming through. So this represents V2, this represents V1. Notice how it bends. This is theta 1. Get some orange in here. There we go. And then this is theta 2, right? So we have theta 1 here, theta 2 here, theta 2 here, etc. We have a couple theta 1s and theta 2s, right? So we notice that theta 2 is greater than theta 1, right? We're noticing that, right? So theta 2 being right here, theta 1 being right here, what we're going to notice is that this theta 1, right, is this angle here, right? See that angle there? That's theta 1 is complementary to this, but that means this is also complementary to this, which means this is also theta 1. Ooh, that's the secret, right? That's the secret, which means this is also, so this was theta 2 here to the normal line. That's complementary to this. And that's complementary to this. So that means this is theta 2. So that means this inside of this triangle, careful, it's this triangle here with this wavefront, right? This wavefront is distinct from the normal line, right? The point is these angles are the same. So the sine of theta 1, and if you look at that geometry and you draw it big enough, you'll convince yourself that that's theta 1 and that's theta 2, right? So what's the sine of theta 1? Well, it's the opposite over the hypotenuse. What's the sine of theta 2? It's the opposite over the hypotenuse, which is the wavelength over that distance d. Distance d along the boundaries between where the wavefronts hit. That's kind of cool. So that means d equals d, which means lambda 1 over sine theta 1 equals lambda 2 over sine theta 2. But wait a minute, what is lambda? Lambda in general is v equals f lambda, right? So lambda is v over f. So lambda 1 is v1 over f, lambda 2 is v2 over f, right? So we have frequency is constant. So same frequency. Since it's the same frequency, we can just replace lambda with v because it's just going to cancel on both sides. So what do we get? We get that v1 over sine theta 1 equals v2 over sine theta 2. And this is basically Snell's law, although it's typically written as this. Sine of theta 1 over v1 equals sine of theta 2 over v2. And it just comes from this geometry here, where all of these two triangles share a hypotenuse, where the wavefronts match up, and then this is an input, and this is an input for the new wavefront. These go farther, these are closer, and they share the same distance because that input is creating a frequency, that input is creating a frequency, a compression, a compression. Great. We have our Snell's law. equation. So now we can actually solve for it. And if you might notice, the sine of an angle goes with the angle. So this does indeed confirm that if velocity increases, theta increases. If velocity decreases, theta decreases. But also, if theta 1 increases, theta 2 increases. And if theta 1 decreases, theta 2 decreases. So let's look at some examples. We're going to have another video with some examples. We're going to do examples in class. So there's a few things I want to go through right now. First is this. One is if you have like a circle, right, like this, the normal lines go to the center of the circle. So say I have, right, rays coming in like this. This would have a theta 1 of 0 degrees. This would have a theta 1 of like 30 degrees. And this would have a theta 1 of 30 degrees. And say V2 is greater than V1. So theta 2 is greater than V1, sorry, is greater than theta 1, right? For example, then if there was no speed change at all, it would go straight through. So this is going to bend outward. So we need to compare this and bend this outward like this. So theta 2 is greater than 30. Here, it being 0 is the one example we're going to see that if theta 1 is 0 degrees, the sine of 0 is 0. So it's 0 on both sides. Then theta 2 is 0 degrees. That's the exception. This is the vertical line theory. The vertical line exception, where if the ray is the normal line, then it just keeps going straight on through. Here it's going to bend away because theta 2 needs to be bigger. Remember, it goes through the normal line. It does not reflect off. It does not reflect off. It goes through the normal line, and in this case, it's going to bend outward. If it bent inward, it would come close like this. So if it bent inward, it would come something like this. It would come something like this. But in this case, we wanted it to bend outward, so I'll erase those, and I'll erase what's wrong, and just make that nice and clean. Boom. Let that make sense. Everything I just did, let that make sense. Therefore, this, therefore, bends outward. Part 2. I'm going a little quick, right? But I'm just wanting to get these things down, right? So say I have a boundary. Say I go from air to water. Water has a velocity of 1483. Air has a velocity of 343. So velocity 2 is greater than velocity 1. Great. By about a factor of 4.5, 4.4, right? So the angle won't be multiplied by 4.4, but the sine of the angle will be. So that's a big change in angle, right? So here's my normal line. Step 1, draw the normal. Step 2, let's draw some theta 1. Let's say theta 1 is 30 degrees. If I solve for this, what I get is sine of 30 degrees over 343 equals sine of theta 2 over 1483. And if I do this math, first of all, make sure you're in degrees, everybody. Make sure you are in degrees right now. I'm in degrees. Awesome. Sine of 30, I know that to be a half, right? That's an easy one. Divided by 343 times 1483. What you're going to see right away is that sine of theta 2 is 2.16. So that means theta 2 is indefined or undefined. You can't have a sine of an angle be greater than 1. So what happened? Well, what happened is that this refracted so much that theta 2 is bigger than theta 1, right? Because the velocity got bigger. Great. This got so big, the wavelengths got so large that there's no geometry that'll work. This is impossible. There is no geometry that works in this case. So this reveals that there is no angle of refraction. This mathematical impossibility reflects a physical impossibility, and that's pretty cool. So that means it doesn't go through. So if the sine of theta 2 is greater than 1, there is no refraction. And I hope that makes sense because I think that makes tons of sense. And that's kind of really awesome that the mathematical impossibility reflects a physical impossibility. So there is no geometry that works to allow the wave to go through the medium from one, sorry, if it goes through the boundary from one medium to another. So what happens is that the wave has to come back. It becomes an impassable boundary. And what happens is it just reflects. And reflection is where theta 1 equals theta 2 in the same medium. And of course, if you have the same medium, you have the same velocity, you have the same wavelength, you have the same angle. This is called reflection. I always kind of joke, but also seriously say that reflection is the easiest thing in physics because you have this, everything's the same, and it just is a nice, neat reflection of itself. Right? So reflection is where it bounces off the boundary and comes back into the same medium. If there's no geometry that works, which happens, of course, if sine of theta 2 is greater than 1, there is no refraction and you get reflection. This is called total internal reflection. Please understand what this is. It's due to this, right? It's due to this logic. Please know this logic. Pause the video, rewind it if you need a refresher, if you need a review, but total internal reflection. Boom. TIR is when theta 2 or the sine of theta 2 is greater than 1. So when is the sine of theta 2 greater than 1? Well, that means that theta 2 is greater than 90 degrees, which of course is impossible for refraction, which means that there's no refraction. It's just reflecting back into the same medium. I'll refer you to the picture on the other side I just drew if you want a picture of this. But here's the math. Math of TIR, total internal reflection. So what do I get? I get sine of theta 1 over V1 equals sine of theta 2 over V2. But sine of theta 2 is greater than 1, right? So if sine of theta 2 is greater than 1, I'm going to solve for when it equals 1, right? And realize that if theta 1 is greater than some critical angle, because of course, if theta 1 increases, theta 2 increases. So as I increase this angle, theta 1, if I start off like this and I keep increasing it, theta 1 keeps increasing, theta 1 keeps increasing, theta 1 keeps increasing, then theta 2 will begin to increase, and eventually theta 2 equals 90 degrees. When theta 2 equals 90 degrees, we've reached that boundary of TIR. So theta 1 equals the critical angle when theta 2 is 90 degrees. And if theta 1 is bigger than that critical angle, then theta 2 is greater than 90 degrees, And of course, we get TIR, we get the impossible situation for refraction to happen. So here's how we solve for it, right? We get, you can pause that. I hope that made sense. My little scribbly diagram down there. I hope that made sense. Um, when theta 2 is 90 degrees, we can just say, okay, sine of theta 1 over V1 equals the sine of 90 degrees, which is 1 over V2. So that means I multiply by V1 on both sides, and I get that the sine of theta 1 is the sine of the critical angle, I should say, sorry, is V1 over V2. So you can just use Snell's law and this logic here. What's in a box is the most important part. So the critical angle is when theta 1 equals the critical angle when theta 2 is 90 degrees, and it's the border of that impossibility. And then you just get that the sine of the critical angle equals V1 over V2. So notice for this to happen, V2 needs to be bigger than V1 for that math to actually work. You won't get a critical angle if V1 is bigger because you can't have the sine be greater than 1. It all works out. That, my friends, goodness, look at all these good slides. Please, hi, go through it all. Sorry if that was quick. I wanted it to just be a quick video, but I also wanted it to be complete. Please rewind it, take good notes, right? Draw those drawings, follow the logical progression. I hope I outlined it clearly and we can practice in class. May the waves be with you.